Okay, alright. So let's back to Newton's third law. Nikki, you are with your example. You have some idea about your example now.
If I push the
Yeah, if you push
I
D.
have the
Okay, if you punch D.
yeah, then
So
you have the
Which force?
no, I will have the like action and he'll have the reaction.
Okay, so the action is from where to where? From what to what?
Hitting to me.
You hitting Dean is the action force.
Yeah.
Okay, what about reaction?
The feeling.
Dean feeling is the reaction.
Like he like this,
Dean
this-
feeling
this
is the
action
reaction,
is-
or you feel Dean push you back is the reaction.
yeah. That's the last one.
Isn't that
Last one.
Okay, so for Newton's third law, there is always involved two objects. It's the interaction between two objects. So, sorry, third law. For every action, there is an equal but opposite reaction, right? So in symbol, we use A and B. We use A and B. So if A exert a force on B, which is FAB, then in return, object B will give A an equal but opposite reaction force, which is FBA. Sorry, FBA. Questions? FAB is the force on A by B. Yeah, if according to this thing, it's the other way around. Okay. Alright, so in the big picture, if every force in the universe has a reaction force that is equal but opposite, so the sum of the forces in the whole universe is 0. Because for every force, you always find another reaction force, right? Even if Mr. Kai is waving my hand right now, there's air resistance, right? There's air resistance. So why are there acceleration all around us? Oh, what's my big answer? Why? If you saw it, you saw it. You don't have to pretend you didn't saw it. Why are there still acceleration all around us? If you can always find an equal but opposite force, according to Newton's third law, then why can we still accelerate things? Oh, so you didn't saw it. You didn't saw the answer. No. No. Pardon me?
It's not acting on the same object.
The action and reaction is not acting the same object. Exactly. Very good. So, according to Newton's third law, you see it's always two objects. One object A exerted force on B, and B in return exert another same magnitude but opposite direction back on A. The two equal forces are on two different objects. You cannot cancel out two forces that's acting on two objects. You can only cancel out forces only if they are acting on the same object and they're equal in magnitude, opposite in direction, right? So, because each force of action-reaction pair acts on a different mass, right? When you say that, okay, acceleration is 0, it's only when you do the forces adding, let's say F1 plus F2, the net force is 0. But how can you do this when F1 is acting on object 1 and F2 is acting on object 2? You cannot, because they're separated. Does it make sense? Okay, very good. Alright, so let's do an example in terms of Newton's third law. Alright, let's think about this. When you push on the door with 10 Newton, should be capitalized. The door pushed you back with exactly the same 10 Newton, but in the opposite direction. Why does the door move and not you? Discuss. Give you 1 minute to discuss, and then I'll randomly draw a person to share the answers.
I get the reaction by pushing that, it pushes by the
It's because the reaction force is happening on this door.
So if I push the door, so that's also pushed by the that's what makes sense. That means I'm getting action and force
Oh. Only after the reaction.
Aaron, why don't you share with us what did you just discuss?
So if I push the door, the door have I have the reaction first with the door pushing me back, but the door doesn't have the reaction force. So
The door doesn't have the reaction force?
like it's it only has the force that it's given by me.
So the only force acting on the door, you mean, is the 10 Newton force
Yeah.
that you push the door.
Yeah.
So the door doesn't have gravity?
The door.
The door has the gravity, so then the 10 Newton
Oh,
force is
yeah.
not the only force that you give to the door, because the door has
Oh, yeah.
gravity and the 10 Newton force.
Mm.
But go on.
Yeah, and cause I can handle the 10 Newton because my weight and stuff can hold the reaction force against me, and but the door will move because it's light.
It's okay, so door is
Door
not
is
heavy
heavier.
enough. You're heavier than door, so that's the reason why door moves and you're not moving.
我不敢苟同你的观点。我们的 was higher than 10 newtons. Why you can push that to the next
Luke, you got something to say?
Yes.
What do you want to say?
Because 那个轴叫什么
Axis?
The axis connected to the door is lower friction than the force you apply to the door, where your shoes and your legs can't hold the 10 newtons that the door exerts to you, so you don't move and let the door move.
Okay, so basically we have the door here. When you push the 10 Newton force, right, your finger gives 10 Newton force to the door. Now, so on this door, there's a 10 Newton force. What other, is that the only force that the door has? No, of course it still has gravity, right? The gravity. But of course, it also has reaction force or normal force to balance out the gravity. Otherwise, the door would just fall, right? But the door isn't falling, so there's normal force to balance out the gravity. But in this direction, horizontally, are there any forces?
The axle.
Okay. So, first of all, we have to understand that the 10 Newton, even though they are equal, but they're acting on two different objects, so they cannot directly cancel out each other, right? So 10 Newton force acting on the door, that's door's 10 Newton. 10 Newton reaction on back to your finger, that's 10 Newton on your finger. Those two, because they're on two different objects, you cannot cancel out. And secondly, each body acts in response only to the force acting on it. So if we just look at the door, if we just take the door as, we don't care about this, we only know that the door has 10 Newton force acting on it. F equal to 10. And then weight and normal force cancel out. Even if there's friction, there's only like
Very
small amount of air resistance, or maybe a friction within the axis, or this is called the hinge. Within the hinge, right? So this friction is super small, not big enough to overcome this 10. But for you, why you're not moving? Well, you're standing on the ground. You're standing on the ground. The door pushes you with 10 Newton force. But why you're not moving? The ground gives you friction force. That's great enough. Is this static friction or dynamic friction? Static, because you're not moving. Clear? Okay. So let's just do one example. The rest of the example you can read it from home. All right, and then our old friend, collision. So, first of all, let's define a system. So we define a system as a collection of more than one body, mutually interacting with others. For example, if I define those two persons as a system, then if I apply a force on Ashley, we say that this system has an external force acting on the system because I don't belong to the system. Me is outside of the system. So I apply a force on the system. This force is called an external force. But within this system, let's say you push each other, this is what we call the internal force, right? Because it's the interaction between the members within the system, right? So that's not an external force, that's internal force, okay? So everything that happens within the system is what we call inside, or the interaction is internal force. If the force is provided by something that's outside of this system, that force is external force. Straightforward, right? Okay. All right. So, for example, 3 billiard. Is that how you're gonna pronounce it? Billiard balls interacting on a pool table constitute a system. All right. So the action-reaction force pairs between the balls are called the internal forces because it's within the system. However, for any system, all internal forces will always cancel out. Why? Why are, for any system, all internal forces will always cancel out? Momentum. Conservation of momentum? The forces, why can forces cancel out? They're like action-reaction. They're acting different object. We just talk about if you're within the system. We're considering them within the system. As a system as a whole, now we're talking about the system, right? So this force, even though the forces is acting on different objects, but those objects are all belong to the system. So we look at the system overall. The internal forces always cancel out. Does that make sense? Any questions? Okay. All right. So let's quickly run through this. The internal force pairs only exist while the balls are in contact with each other, when they are collide with each other. For example, like this, right? The white arrow here represents the forces provided by the white ball to the red ball or to the green ball or blue ball, right? Okay, so notice that the blue force and the red force acting on the white ball. So this one here, the blue force and the red force, are they action reaction? Is red force and the blue force here action or reaction? Are they a pair of action reaction? Why not? What's the key feature for action reaction? Number one, it must be equal but opposite. First of all, is it opposite? It's equal, right? Look at the size. The length is equal, but are they opposite, first of all? No. Second of all, action reaction must acting on two different objects. Are those two acting on two different objects? They're both acting on the white ball. That's one single object, so they're not action reaction. Right? Then can you identify action reaction here? Okay, Lindsay, give me a pair of action reaction. The blue ball and the white ball. So this here. Can you give me another one? Okay. First of all, they're equal and opposite. Second of all, they're acting on two objects, right? All right. So, okay. Jocelyn, would you please read those three notes here for me?
Note that the blue force and the red force act on the white ball. The white ball responds only to those two forces. Note that a single white force acts on the red ball. The red ball responds only to that single force. Note that a single white force acts on the blue ball. The blue ball responds only to that single force.
Okay, thank you very much. Okay, so what about external forces? So external forces are the forces that the ball feel from the external origin, not from each other. Cool. So any examples for the external forces that they can feel, not from each other?
The other ball is actually not.
Gravity, okay, because that's caused by the Earth. And we don't count Earth as part of the system here, right? Okay, what else?
The table for the ball force.
Okay, normal force provided by the table, sure. What else? Friction, yes. Because the friction is also provided by the table, right? Between the ball and the table. What else? Air resistance, or when you heat it, right? When you heat it, the force that you provide is also an external force. Okay, good. So, this we have already learned in MIP, right? Do you still remember what's momentum? How to calculate momentum, Alice? P equals to mv. Is momentum a vector or scalar? Okay, so it's, where does momentum inherit its direction from? From velocity, right? Because P equal to mv, m is a scalar, doesn't have velocity, doesn't have direction. So only velocity has direction. So the direction of the momentum comes from the direction of the velocity. Okay. So let's look at what's the connection between Newton's second law and momentum. As you already know, linear momentum P is defined as the product of the mass and its velocity, which is P equal to mv, right? Its unit obtained directly from the formula are kg and meter per second. Kg meter per second. Let's look at this example first. What is the linear momentum of 4 gram nano SS 109 bullet traveling at 950 meter per second?
The stars.
Let's say Thomas.
It's 3.8 kilogram meters.
3.8 kilogram per meter. That is correct. Very good. Don't forget to convert the units. Okay, let's look at the relationship between Newton's second law and momentum. How do we write Newton's second law? F equals ma, alright? How do we define acceleration? A equals, if we plug in this, so we're gonna get m times short. Right? Okay. I don't like divided by something, so let's times delta t from both sides. Now we're gonna get f times delta t equal to m times delta v. What is m times delta v? What is f times delta t? Impulse. So changing momentum, which is impulse, is related to Newton's second law. Okay, I have a question to ask. In general, am I being too fast or too slow or moderate? Okay, if you feel embarrassed to say, you can come to me later and tell me if it's faster, too fast, or too slow. I'll adjust my speed. But if nothing yet, I'll just keep my current style. All right. So here, as we just derived it, F net can be written as changing momentum divided by changing time. Right? That's Newton's second law in terms of the momentum form. So let's do this example. A 6 kilogram object increased its speed from 5 meters per second to 25 meters per second in 30 seconds. What is the net force? Of course, the traditional way is you can calculate the acceleration, but if you're going to use this equation, how are you going to do it? Alicia, how would you do it if you're going to use this equation? How do we calculate change in P? Okay, so M is, change in V is, change in time is, right. Okay, so 25 minus 5 is 20, 6 times 20 over 30, so it's 4, right? 4 Newton. We're good? Okay. Now, kinetic energy in terms of momentum. How do we calculate kinetic energy? Ashley. Alice. 你忘了？ G H T A B C D E F G mv squared. Okay, so momentum equal to mv. Kinetic energy is mv squared. How can we use maybe momentum to represent kinetic energy, or using kinetic energy to represent momentum? What can we do? I'll give you 2 minutes to find out the relationship between EK and P. Use P to represent EK. Let's say EK equal to watt P.
What?
2 minutes. I would say so.
1.5。
这个是对的。Because I'm asking. Okay, let's assume you don't know velocity. How about that? You don't know velocity. You don't know velocity, which means your formula should not contain any v. Your formula shouldn't have any v in it. Mm-hmm. Okay. Did you get this? P squared over 2m? Okay, good. So we don't know v, so we can represent v by this. And then we just need to plug it in. And then cancel out common term. So we get 2 p squared over 2m. Too easy, don't do it. Okay, collision. Alright, let's start from here. So for collisions, let's consider 2 colliding pool balls, right? One is here, one is there. If we consider this as a system, right? This is a before phase, right before they collide. This is after. This is during, right? During collision. This is after, right? Do you still remember when we learned about collision, we also have before and after, right? Okay, so we have those 3 phases. Now, a system boundary is the area of the interest used by the physicists in the study of complex process. A collision could be a complex process. That's the reason why we use a dash box to emphasize this is the system that we're going to focus on, because there are going to be another factors interacting with it, and we wanted to simplify and to concentrate on this system. So this is what we call the system boundaries. It's also going to be useful when you learn thermodynamics in B4 for HL students. Okay. A closed system has no work done on its part by external force. Now, let's look at those 2 balls colliding closely. Alright. If we plot the force versus time. So when we just collide, when they just touch each other, right before they touch each other, does it have force between them? Before they touch? No. When they just about to touch but not touching yet. still no force, but they're about to have force, right? Then just one moment after they touch, a very short moment, there's gonna be force, right? But this force, is it still small or is already very large?
Not that much.
It's instant.
If there is a during phase, right, it still takes a little bit of time, even though it's very fast, right? It still takes time. Like think of it as like two water balloon, right? Or two soft, let's say tennis ball. Instead of using the hard ones, let's use the tennis ball. When two tennis balls at this position, do they have forces interacting with each other? When they just touch but not touching yet, so 0. Next moment they just touch, so they have forces, right? Okay. The next moment they're still gonna continue to press each other, right? So compared to last moment, is right now the force is gonna be greater? Let's say they still have velocity, they still have not stopped yet, so they will keep squeezing each other until they stop, right? So until they stop, this force has a tendency of, when they just touch, until their velocity stops, the force is increases. The forces between each other is increases. Why? Because there's more shape got changed, right? So if there's more shape change, then you need a larger force. Does that make sense? Okay, so until it stops, the force is going to be the greatest. So this here, the force is the greatest. That means the velocity has been decreased to 0. And now, their force starts to decrease. Why is their force starts to decrease after reaching the 0 velocity?
Trying to get back.
They're going to bounce back, right? As they bounce back, the distance between the shape is gradually regaining, right? Gradually regaining, so the force is getting smaller. And at the moment that they lose contact with each other, the forces disappear. Can you imagine that? Everything clear? So this is during phase, this is before phase. And this is after phase. And this during phase is a very short of moment, right? Very fast. Do we have a problem understanding stuff here? All good? So if we draw the forces, before they touch each other, there's no force, right? Until they touch each other, very short amount of time, force first what? And then to 0. This is the before phase, everything is 0. This is right when they're just about to touch each other. And then forces starts to increase. And then this is the moment where they stopped, relatively, momentarily stopped. And then decrease. This is the during phase. And then after that, there's no force. When they detach from each other, there's no force. Is this okay? We're good? Any questions? Okay. So, notice that there's a perfect symmetry of the red and the blue. What does the red represent? The force on B provided by A, right? The force on B provided by A. Why are they perfect symmetry to each other? Newton's not cancel out. Newton's third law, action and reaction. You cannot cancel out action and reaction because they're acting on two different objects, right? They are symmetry here because there are forces, their action and reaction, they're equal and opposite. See, they're always equal in magnitude, but in different directions, but opposite. You cannot cancel out them because they're acting on two objects. Okay? questions for me? So far so good? Okay, so when we plot this graph, let's think about it. Whenever we have a graph, we are always going to look at some important property of the graph. What could be the important property of the graph? Okay, axis, so y-axis represents force, x-axis represents time. What else? Gradient. In this case, gradient of the graph is basically changing y over changing time, right? Or slope. Changing y is force, divided by changing x, which is t. We haven't learned what is f over t yet, so in this case, it doesn't make sense to us. What else other than gradient? Area. How do we know what does the area represent? If slope is changing y divided by changing x to represent it. Area is basically whatever your y represent times whatever your x represent. So your y represents force. X represents what is force times time? Impulse. So the area under FT graph is impulse. Okay? Alright. So the area of the force time graph, of the force time curve, is impulse. Okay? And here, impulse, we use J to represent it in dp, not I anymore. Why? Well, because I in dp now, for HL student, represents moment of inertia. So we need to use a new letter, which is capital J, to represent impulse. Please take down this note. J equal to F delta T, where J represents impulse, and it is the area under the FT graph. FT graph. Any questions? Questions for me? No? Okay, let's move on. Changing momentum is also the area under the FT graph, okay? Because impulse is changing momentum. Okay. Y is one area above x-axis, another below x-axis. Opposite direction. Don't forget impulse is also vector. Okay, let's look at this example.那就上到这儿，作业。A2 homework.
You actually, are you joking? You actually thought they seriously? What? We're just joking now.
So homework is page 2. Oh wait.
No, man, I told. I2. Norman.
I don't give it. I don't give a shit.
Order for AS.
Give it.
选择题做完，18道选择题，选择题做完。 Everybody got one? See you on Thursday. Okay.
Actually, this kind of like extra restriction. More of a nursing she's so pretty.
He does that to everyone.
现在就可以，应该是我找到了我。哦。